Hello, my name is Christos Monokrousos. I'm working for TÜV Rheinland as a Global Segment Coordinator for Solar, and today I have the pleasure to talk about extended bankability. It is a very important topic because it can differentiate from PV modules which make money, in other words, which are bankable, from PV modules that do not make money. What I have for the agenda today is, first of all, I would like to introduce you to some basic, let's say, fundamental concepts for PV module reliability. Then I will review the advantages for testing with TÜV Rheinland. I'll present your test protocol and close with how do we benchmark modules based on our protocol. And now I would like to review the advantages of testing with TÜV Rheinland. TÜV Rheinland has more than 40 years of experience in solar, in photovoltaics. We have been performing power plant inspections since 1990s. We are active in more than 500 locations around the world and in 59 countries. Our labs operate 9,000 square meters of area. We employ more than 130 experts in solar. And overall, we have inspected over 250 gigawatts of PV projects around the world. And what we offer is tailor-made solutions for manufacturers, EPCs, investors along the value chain globally. So PV modules are produced and sold with an expected warranty that exceeds 25 years. And the majority of the manufacturers claim that this is based on certification. But is certification a reliable indicator of module lifetime? We see issues with fielded modules, such as backsheet failures, delamination, corrosion, moisture ingress, and also power degradation, power loss. And often these failures manifest in the first 10 years of performance in the field, or even less. In this background, banks and developers have now started requiring extended reliability testing prior to project and supply contract approval. What I'm showing you here is the bathtub lifetime curve. The vertical axis represents failure rates, and the horizontal axis represents field exposure. In the first 1 to 2 years, 1 or 3 years if you like, of module performance in the field, we have early field failures which are associated to the PV module design. Then we have the useful life of a PV module, which, depending on the quality of the manufacturing, maybe 20 or 50 years, of also much less when the quality is not adequate. But there are also cases that can be extended far more than 25 years. And in the end, we have the end of life, where failures are mostly related with the endurance of the materials involved and the processes involved in the manufacturing. These failure rates, of course, they will increase exponentially till they exceed the module warranty limit. Qualification testing according to 612.15 and 670.30 aims to capture failures which are related to the PV module design, let's say, to failures which manifest in the first years of operation of PV modules in the field. Extended stress testing, according to ICTS 63209-1, aim to capture failure modes which develop during the middle or the end of the module's lifetime. So to answer what we questioned before, doing certification according to 612.15 and 670.30 is not a reliable indicator for PV module's lifetime. Doing extended stress testing is though. So 30 to 40% of new construction includes performance estimates that go beyond 30 years. They may reach 30, 35, 40 years, or even more. Independent engineers are typically asked to validate these estimates. But without testing data, independent engineers' degradation estimates can often exceed 1% per year after the first 25 years of performance. The emergence of innovative module designs and technologies necessitates advanced reliability testing. This proactive approach is essential for validating degradation assumptions in financial model and also securing independent engineer signatures. And now I would like to talk about what are the advantages of testing with TÜV Rheinland. So first of all, there are market problems. Manufacturers often complain that it takes way too long to complete an extended stress protocol. There are also multiple labs, and often I hear complaints that they have no single point contact, which is also recognized globally. And I have also heard complaints from consultants who say that there is no appropriate testing scheme to assess the long-term reliability of a PV module. Our solutions to these problems are: we offer improved lead time that can compress the testing time of a reliability protocol down to 6 months. We provide a single touch point, and you can have access to all our labs worldwide, which are also recognized worldwide. This is very important. And also our extended stress protocol is based on an IEC standard, a test specification 63209-1. This is a standard that's already published for several years, specification precisely, and generally has a technical maturity, and it is a well-developed, I would say, standard. What are the targets and the benefits when you test with us? So you have access to labs in the US, Germany, China, and India. You can benefit from integrated solutions which combine audits, basic certification, extended stress testing, and if you put many things together, you can have reduction both cost and lead time. And last but not least, you have access to our experience that goes back to 40 years of testing and certification in solar. I would now like to present the Extended Bankability Protocol. It is based on IEC-TS 63209-1. Sequences 1 to 5 are taken from there. And then we also add some critical points to these standards. We also capture our experience in the field. So generally speaking, it consists of 7 mandatory test sequences, which are able to detect all relevant failure modes that may happen in the field. We also have one optional test sequence, which provides reliable test data and can allow us to perform an accurate and correct energy yield prediction. I would now like to take the time to talk a little bit about each test that we do in the test protocol. Test sequence 1 and test sequence 4 are sequences engaging thermal stress and humidity ingress. So thermal stress is done by repeating thermal cycling 203 times, and humidity stress is done by repeating damp heat 1002 times. Generally, PV modules are constructed as a laminate of different materials with different chemical and thermal properties. The material durability sequences probe how the material react to temperature stresses and humidity ingress. Thermal mismatch between different materials can lead to unforeseen chemical and mechanical degradation modes. We perform long thermal cycling, which tests the endurance of solder bonds in a PV module and simulate damage which will be sustained in a PV module due to changes of temperature. And last, the extended damp heat is targeting hydrolysis accelerated processes that test the durability of polymeric materials such as edge sealant, junction box, and backsheet, but also may trigger solar cell corrosion. I'm moving now to sequence 2, which is assessing the mechanical endurance. So previously, when we tried to do it while we were working in IEC, we tried to develop a test sequence which was solely dependent on dynamic mechanical load, or cyclic load if you prefer. Unfortunately, we were not able to reproduce results which were, let's say, consistent with the observation that we have made in the field. Therefore, now we have added a static mechanical load testing in the beginning, prior to cyclic mechanical load, which initiates the crack and exposes module susceptibility to mechanical damage. Dynamic and mechanical load expands the cracks, which helps isolate cell regions and leads to a better estimation of real-world power chains. And then in the end, we do TC50 and humidity phrase 10, which applies more stress on the cracks, interconnections, and other materials after the mechanical load. And as you can see on the pictures on the bottom, basically the failures that we saw in the lab are similar with failures that we have seen in the field. I would now like to talk about sequence 3, which is a backset durability sequence. So together with colleagues from CFV, also others participating in IEC TS6 3209-1, we have produced a state-of-the-art backset durability test sequence. Backsets are the first line of defense for a PV module. It is shielding the module against moisture ingress and also provides electrical insulation. We have seen backsets with correct polymer processing that can endure in the field for more than 25 years, but we have also seen bad examples that involve poor manufacturing processes and low-cost additives that can produce a backset with suboptimal performance, leading to cracks, loss of electrical insulation, and ultimately power loss and also fires. It can also lead to catastrophic failures. And you can see here that the test protocol that we have proposed that combines damp heat with a combination of UV thermal cycling and humidity freeze that can adequately reproduce the failures that we have seen in the field. And here I'm showing you an example of a polyamide backset which shows cracking, and the picture on the left is taken from the field. And this is again the same backset. After the backset durability protocol, it shows the same problems. So I would say this is also a very successful test protocol. PID, so this is sequence 5. PID basically comes from the difference in voltage between the cells and the frame. When you have ions accumulating to the glass, they migrate through the glass down to the cell, and as they progress, they corrode and they often create shunts. Here we're using the PID stress protocol, which is also available in 6.12.15, but for a much longer duration. We test for 192 hours. It's extended duration. Tests are carried out at 85% relative humidity and 85 degrees Celsius, while the voltage between the shorted terminals and the frame is system voltage. Generally, it is understood that 192 hours of PID can effectively capture PV module times. I would say it's a very severe test. And they can identify modules which are susceptible to PID. UVAD is a new degradation mechanism which is relevant for TOPCon and heterojunction cells, for new technologies. So UVAD means ultraviolet induced degradation, and identifies the susceptibility of solar cells to UV radiation, which may cause degradation due to deterioration of surface passivation. As I have already mentioned, UVAD is more common in new technologies such as TOPCon and heterojunction. compared, for example, to older technologies such as aluminum back surface field or even PERC. You will have a lot more UVID in these new technologies. So the test protocol here is testing whether PV modules can withstand a severe dose of UV, so 120 kilowatt hours per square meter at the front and another 60 kilowatt hours per square meter at the rear, without showing significant degradation in the end. LETID, light at elevated temperature induced degradation. So this is specifically targeting PERC technologies. We have seen that some PERC technologies have been shown to be susceptible to a degradation mode called LETID, which may lead up to 10% efficiency loss. LETID occurs at elevated temperatures exceeding 50 degrees Celsius under illumination, and it is possibly due to hydrogen diffusion in the bulk of hydrogen related to defect activation. These are effects which colleagues from UNSW have studied and published several papers. LETID is causing a reduction in minority carrier lifetime, which manifests as a loss of performance in Pmax and VOC. Recovery may occur following LETID degradation, but the recovery is very slow, and while PID develops in the first 3 to 5 years of modules in the field, recovery may take much longer, 5 to 10 or even 15 years, and modules may still recovering. I would now like to talk about performance testing for energy yield. Silicon-based PV modules show different performance characteristics, have different performance under different conditions of irradiance and temperature, but also different angles of incoming light, but also spectral response as well. So here we practice performance measurements to conduct accurate energy yield predictions. Independent engineering energy yield prediction must be based on concrete data. So TÜV Rheinland laboratories have very high intercompatibility with mean variations within 1%. We utilize 61853 series of standards, DAS1 to DAS4, to perform these measurements. And testing is done utilizing AAA+ solar simulators that can achieve an uncertainty at STC which is better than 1.6% at STC and better than 2% in the full range between 100 to 1100 watts per square meters and 15 to 75 degrees Celsius. Benchmarking. So TÜV Rheinland certification on the extended bankability protocols also comes for a test mark, which provides a better visibility of our certification to the manufacturers. We differentiate modules between superior performance or top performance, if you like, and modules that have passed the protocol. Passing the protocol, I have to say, is not an easy thing to do. So passing the protocol also shows that the module has high quality. But we also differentiate, like I mentioned, between the top performers that they have degraded very less and ordinary modules of high quality that pass the extended bankability protocol. The superior performance are also listed in TÜV Rheinland website, and the total lead time for benchmarking is 6 months. To conclude, the 2PFG, the internal standard of TÜV Rheinland 2PFG 2940, called Extended Bankability, is a test specification developed by TÜV Rheinland and based on IEC TS 63209-1. It is designed to distinguish between various types of PV modules based on their potential to generate revenue at the power plant. The test protocol consists of 7 mandatory test sequences, which assess the reliability of PV modules, and 1 optional, which assesses the energy yield performance of PV module. Certified PV modules receive a test mark, and their names are listed in TÜV Rheinland website. It also possesses synergy that can be upgraded to a quality control scheme, where both production line monitoring and supply chain audits take place as well. If you're interested in this presentation, then I would encourage you to follow us on social media. And with this, I'd like to thank you very much for your attention. It's a great pleasure for me to give this talk today.